Okay, so in the previous video, we talked about the idea that sodium plus is something that sodium likes to form, and Cl minus, chloride, gaining an electron is something that chlorine likes to form. So what about these charges, right? Do we accept having positive and negatively charged stuff just hanging around out there? And the answer is no, we don't. That the universe does not really like positive stuff sitting all by itself. But if we take a sodium plus and we take a Cl minus, Na plus and Cl minus, and we bring them together, the positive on the sodium and the negative on the chlorine will cancel each other out to form sodium chloride, which is common table salt. And this idea of taking positively charged ions and matching them with negatively charged ions is the basis of the first class of matter of compounds that we're going to be looking at, which is ionic compounds, compounds formed by ions. NaCl is not just used as table salt, it's essential in the body. The nutrients that are these ions, Na plus and Cl minus, are both really important electrolytes, electrically charged particles in our biology. And so what about if we have the following case? Let's say we have calcium, which is Ca2+. And again, here it's really important to understand the charge on the chemical species. When we look at calcium and someone says, oh, let's form an ion of calcium. Well, that's calcium 2+, because calcium's in the second group. It will lose 2 electrons to form its noble gas, calcium 2+. If we want to match it with chlorine, well, we have a bit of a problem because chlorine is Cl-. And if we match Ca2+ with Cl-, well, we're not going to cancel out those charge. But that's no big deal because we can take one calcium ion, Ca2+, with 2 chloride ions, Cl-, to form calcium chloride by showing CaCl2. And this notation here is really, really important. When we look at the ions, we notice that the charge with the sign is in the top right. For our compound here, calcium chloride, CaCl2, the 2 that denotes that it's 2 chlorines to match with the calcium is in the bottom right. This is really universal notation. It shows that these are bonded together and form up a single compound made up of calcium 2 and 2 Cl minuses. And this is important as well. But really when we're studying chemistry, looking at calcium and chloride and knowing that they come together to form this compound is essential for this chapter. Okay, when we look at compounds, we want to be able to predict the charge of the most common ions that we have. So take a minute here, pause, and write the charge of the ion that each of these most commonly forms. And if you can, go ahead and show the symbol for that as well. Just like we showed for chlorine, it was Cl- for its ion. Okay, taking a look at these, here are the answers to the different ones of these ions, potassium K+, and so on, right? We get these by noting that this is the number of electrons that need to be gained or lost in order to form a noble gas, and so these are the common ions that each of these is going to make up. What about if we have the following combinations, right? And here we see some familiar faces from previously, K+, S2-, etc. Which of these are going to make, or should I say, what formula of ionic compound are each of these going to make? And remember that when we match up the cation, positively charged ion, with the anion, negatively charged ion, we need to cancel out all that charge. Show the ratio in a great chemical formula. All right, hopefully you're able to do that. Here are the answers, and I hope that you were able to get these as well. This, again, is ionic compounds. It's a really important class of molecules and is essential to be able to take our initial metals and nonmetals, that's what makes up ionic compounds, predict the charge, and then form what the compound is going to be from those charged ions. Okay, finally, now that we have made our ionic compounds, let's do some naming. So the naming is pretty straightforward. We're really just focusing on what the two ions are. So the first thing we want to do is we want to name the positive ion first. This is usually the metal. So if we have NaCl, we say, oh, Na, that's sodium, Cl is chloride, sodium chloride. We don't mention the number, we don't mention anything like that. NaCl, sodium chloride. And that's the second thing that we do, right? We name the negative ion second, and it's usually a nonmetal. We change the ending to "-ide", and there we are. If it was sodium Na+ with oxygen, O2 minus, oxide, it would be sodium oxide. If it was with sulfide, it would be sodium sulfide. And even if we have sodium with oxide, it would make it 2 sodiums to go with 1 oxide. It's still sodium oxide. We let the number that is the number that makes up that compound not really be emphasized because everything's balanced based on charge. If it's sodium oxide, we know sodium is +1. We know oxide is 2 minus. So if I say sodium oxide, you already know that it's going to have 2 sodiums. So basically leave off all the numbers of how many each one are there when we're naming ionic compounds. Finally, metals do often take more than one possible charge, and if so, they're written with Roman numerals. This is very common with things like iron and the like, and we really just need to show the charge because iron can take iron +2 or iron +3. If we have iron +2, it'll require 2 chlorides, Cl- to match up with it, iron 2 chloride. If it's iron 3 chloride, it'll take 3 chlorides, and we would have FeCl3. These two examples show the differences between iron 2 chloride and iron 3 chloride. This denotes the charge on the iron, and again, that charge is what's going to govern all of the matching that we do with any of these ionic compounds.